A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians, welcome back to another video. And I have a feeling that you are gonna like this one today. A diffy q, cosine squared times y prime plus y is equal to tangent of x. This right here is a G question, and I think it was from last year's JEE Advanced. And I wanted to do an improvised session because I had a very good idea in mind, but I wasn't certain if it would work out. So I worked through the problem, and I think this is my most creative solution to a differential equation yet. And try it out for yourself before watching the video. I think it's a beautiful solution that I came up with, or way of solving it. Let me know down there in the comments how you solved it. By the way, this show is supported by you guys over on Patreon. If you want to help keep the channel stay alive, then please make sure to support the channel on Patreon. It would mean the world to me, and it really motivates me to make more videos. So check it out, linked in the description. And now we are going to dive right in. Now the thing that really piqued my interest here, and where I put my eye on, was the cosine squared. Why is it that I focused instantly on the cosine squared? It's because of the tangent right here. My idea was, since when differentiating the tangent, you're gonna get out the cosine squared in some kind of way. Maybe this yields some kind of solution to the problem, and maybe this is how you also approach the problem before watching the video. So what I did is I said, I'm gonna suppose that there is a solution to this differential equation just being the tangent of x. So let t of x be equal to tangent of x. Now, how is that interesting? Well, we are now going to differentiate both sides with respect to x, giving us overall that the differential of t, so dt dx, is equal to the differential of tangent of x. Differentiating the tangent of x, I went through this time and time again here on this channel, turns out to be the secant squared of x. But what is the secant? By definition, the secant is 1 over cosine. So secant squared, consequently, is 1 over cosine squared. So this yields 1 over cosine squared of x. And this is even more interesting considering that we can multiply both sides by the cosine squared of x under the condition that x is in a domain where the cosine squared, or in other words, the cosine is never equal to 0. This really depends on your boundary conditions. But for now, we are going to multiply both sides by it. We are going to get that the cosine squared of x times the differential of our original function, dx, is equal to 1. Now, do you notice something? We get the cosine squared of our differentiated function, which is the first part. And we also get, if we say that our function is equal to tangent of x, exactly this part. But one thing which is kind of annoying here is this 1 that we get right here. So what we are going to do is we are just going to add both of our equations together. Also, we are going to say that, well, since this really comes close to our original differential equation, we are going to say that y of x is equal to the tangent. Then we get cosine squared times dy dx is equal to 1. And now if we add both our equations together, we are going to get that the cosine squared of x times dy by dx plus 1 is equal to the tangent of x plus 1. And the only bit right here, which is messing everything up, is the plus 1. So how can we get rid of it? Well, by saying that our original function is not tangent of x, but tangent of x minus 1. This doesn't change anything. If we differentiate our function with respect to x, then the 1 is gonna vanish, obviously, as a constant, and we are still going to end up with the same differential that we get right here. With the one difference that if we now add those together, our 1 and negative 1 are gonna cancel, giving us our original differential equation. And now you could say, I'm going to call it quits here, but this is not how diffy q's work. Namely, what we found here is only a so-called particular solution. It's not a general solution to this differential equation. It's just one particular solution which does work out miraculously. Okay, you can solve something like this by looking very intelligently at your problem like I did and see what the solution is going to be. Or you can go through a whole lot of hassle by doing series expansion and the like. There are many different ways to find a particular solution. But here, it just turned out that by observation, you are going to get a nice particular solution out. What do we need for our general solution of the differential equation? We also need the homogeneous solution. Take a look at my differential equation playlist here on this channel. I'm explaining everything there, like the whole theory on differential equations. Check it out. It's pretty good. Link down there in the description. What is the homogeneous solution? Well, this right here is a function of the form p of x times dy dx plus y is equal to another function f of x. The homogeneous solution is just when we set tangent of x being equal to 0. And then everything just falls apart very nicely and then we are basically done. So for the homogeneous one, the homo solution, we are going to get that we need to solve cosine squared of x times dy dx plus y is equal to 0. And now we are going to go through the standard procedure here. At first we are going to separate both sides, meaning we are going to subtract y on both sides. And then we are going to bring everything that is y to the other side and everything that is not with respect to y implicitly to the other side, which is just one side if you consider this side being the other side and this right here is the original side. I don't know. It's mathematics. Fuck off. Now, what we are going to do, obviously, we are going to divide both sides by cosine squared dx, as mentioned before, under the condition that's not equal to 0, depending on your boundary conditions. And we are going to divide both sides by y, under the condition that y is not equal to 0, okay, on our homogeneous solution, but we are going to say that's not a trivial solution. I don't even know if a trivial solution would work out. No, it would not. Then we would get 0 here, and 0 is not equal to tangent of x only for certain values of x. Now we are going to do the divider stuff. We are going to get 1 divided by y times dy dx is equal to -1 over the cosine squared of x. And now we are going to integrate both sides with respect to x, and then we are going to do some black magic physics fuckery to solve this differential equation, and then we are basically already done. Now, in physics terms, if you are an absolute idiot, you can say that the dx is going to cancel out, meaning we are just going to integrate 1 over y with respect to y, leading to the natural log of y. So on the left-hand side, we are going to get the natural log of y plus some arbitrary constant c, but we can bring it to the other side and absorb it in the other constant that we are going to get on this indefinite integral. Now the cool thing is, 1 over the cosine squared is very easy to integrate if you know about what we did before. The differential of the tangent of x is the same as 1 over the cosine squared. Well, meaning if we integrate both sides here, we are just going to get the tangent out on this side, but with a negative sign, so negative tangent of x plus some arbitrary constant c out of the complex Orion numbers. And now, in order for us to solve for our homogeneous solution, we are just going to take base e on both sides, giving us overall that y homogeneous of x is equal to e to the negative tangent of x plus c. But we can make use of the exponentiation properties to turn this into e to the negative blah 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 times e to the c, which is yet another constant. I'm gonna call it e snack as per usual. And now we are obviously done. Now the general solution to our differential equation consists of the particular solution plus our homogeneous solution, or the other way around. Meaning our general solution to this differential equation is going to be e to the negative tangent of x times e snack, and then plus the tangent of x minus 1, where we don't add another constant because this wouldn't work out with this y term that we have here. So just keep this in mind. There is this constant right here, -1, which you can also find out if you don't get the particular solution out through your boundary conditions. This is also one way to get this particular solution here, using boundary conditions or just plugging numbers for y and x in, if you know a bit about your differential equation. And all the other gears and other works around this mathematical structure. And I thank you guys for watching, and I hope you did enjoy what you've seen today. This was a very clever solution, at least in my opinion. Let me know what you think. And if you do enjoy things like differential equations, calculus, analysis, maybe also a bit of algebra, then the contents of today's sponsor Brilliant might be the perfect fit for you. Man, I love myself some differential equations, and as mentioned before, finding out particular solutions can sometimes be very tricky. Sometimes you can't even find nicely a particular solution and you need to use numerical methods or maybe things like graphs to look further into the family of solutions of a differential equation to learn more about it and its mathematical structure at hand. And this is where Brilliant could maybe come in, even for you and your studies. Brilliant is an online learning platform and also app with nearly 70 interactive courses in all topics STEM. It really doesn't matter if you want to start from the ground up and work yourself up to higher mathematics, or maybe you are already a professional in the field of mathematics, physics. Brilliant definitely got something up the sleeve for you that you can use to get you further in your studies. And as mentioned before, Brilliant loves to use visuals in their courses to help you understand the problems at hand better. Easy examples are in their calculus courses. There you can use parameters to vary the function's properties, and those parameters can be varied by dragging on levers and the like. Just take a look at all those animations and you are going to see that Brilliant is seriously something that you can use if you are a visual type learner that doesn't like the abstract stuff that much but still wants to learn higher mathematics, physics, chemistry, computer sciences. And with their course system, it's rather easy to get a grasp of those topics. And if you want to try it out for yourself, you don't want to take my word for it, you want to try it out seriously and see if it's something for you, then make sure to use my link down there at the top of the description, brilliant.org/flammable-maths. With it, you are going to get a 30-day free trial of awesomeness. Try the whole landscape for completely free and see if it's something for you. And if you think like this could turn into a long-term relationship between you and Brilliant, then definitely make sure to make whole use of my link, and the first 200 people to do so get 20% off an annual premium subscription, which is an amazing deal considering how much content they have available on their website already and how much content they are adding on a regular basis. They are also doing stuff like extra Christmas courses and the like. It's just amazing. For special occasions, they also like to add certain stuff to their website and also daily courses and stuff like this. Just let yourself be surprised and take a look at Brilliant today and see if it's something for you. And this would support the channel so much. And I thank you guys for watching, and this concludes today's video. I really like this differential equation. There was a pretty fresh breath. I really liked it, and I hope you did like it too. And about the next video, I wish you guys a flammable day. See ya.